Okay, everybody, this is the first part of our pre-work for our physics lesson tomorrow, or particle motion. I'm on page 71 of your packet, and I want to start by going over this first key lever. This big idea just focuses on the big relationship that we know about between position, velocity, and acceleration. So if you want to think about the stairs that we reference in physics problems, that's what this problem highlights right here. So we have positive time values and we're given a position function for this particle. We're asked to find the acceleration at the point when the velocity is first equal to 0. So the big thing that I eventually want to find is an acceleration, but I can't do that until I first know when my velocity is equal to 0. So just the first thing here, if I'm given position and I want to get down to a velocity, the first thing I'm going to do is take the derivative. So one way to note that is that the derivative of position actually is the velocity function. And if we apply some trig rules, that in this case would be cosine of t plus sine of t. And that's me just using my trig derivatives from up here. Sine's derivative is cosine, and negative cosine goes to positive sine. So I want to know when that velocity is first equal to 0. So I'm going to set that sucker equal to 0 and attempt to do some solving. This is a trig equation, so it's kind of more complicated. So I'm just going to set cosine of t equal to negative sine of t, and see if I can reason my way through this using my unit circle. So my circle from pre-cal kind of helps me to identify the solution to this problem. I want to just look at this, and instead of doing a lot of work here, I just want to pose the question to myself: what angle is it that I run into first where my cosine and my sine have opposite values? So that negative sign, the way I'm interpreting that is, when are these two things opposite of one another? So when I start at 0 and I roll through this unit circle, the first significant place that I notice is right here at pi over 4. That's when my sine and cosine equal each other, root 2 over 2 and root 2 over 2. That would be great if my equation said cosine equals sine. I'd have my answer right there. But I want to know when cosine is the opposite of sine. So I'm going to keep moving, and I find myself over here directly across the y-axis at the value, 3 pi over 4. And I'm drawn to this because that's a perfect reflection of that first angle I talked about. But on this side in quadrant 2, my cosine is negative root 2 over 2, and the sine is positive root 2 over 2. And oh my gosh, that's what I'm looking for. That's when my sine and cosine have opposite values. That happens at 3 pi over 4, which is great because now that I know when that happens, when that velocity first equals 0, I can go address the actual question, which is to evaluate the acceleration at that time. So just a side note, again, using my stairs, if I am on a velocity function right now and I want to get to acceleration, that's going to involve another derivative. So one way of thinking about that is the double derivative of position equals the first derivative of velocity, which now, according to my stairs, I can reference as acceleration. And again, if I use my trig derivatives, cosine's derivative is negative sine, plus sine's derivative is cosine. And all this problem is asking me to do is take that acceleration function and evaluate that function at 3 pi over 4. So this becomes the negative sine of 3 pi over 4 plus the cosine of 3 pi over 4. I've already got that established on my unit circle. So the negative sine of 3 pi over 4 is going to be negative root 2 over 2. Plus the cosine of 3 pi over 4, because I'm in quadrant 2 and my x's are negative, is also negative root 2 over 2. You can do a little bit of math. That's negative 2 root 2 over 2. When my 2's cancel, the answer is just negative square root of 2. All right, our next key lever involves displacement and total distance traveled. This is a really big thing that College Board likes to make sure we understand the difference between. So I'm going to run through these formulas real quick before we dive into this question. Displacement, by definition from a physics course, is a change in position. So displacement is equal to the change in position. And in calculus, the way that we represent changes, remember, is with a definite integral. So anytime we're asked for the displacement, we want to make sure we're integrating from a to b, a function that has an antiderivative related to positions. So that's the velocity function. When I think about my stairs, PVA, the function that I can find the antiderivative of that lands me on the top step is velocity. So a change in position is an integral of velocity. That just tells me at time A, if I'm at this location, and time B, I've moved to a new location, the displacement is the difference between those two positions. Total distance, however, is not just a change in position. It's actually the sum of all my movement. Regardless of if I'm moving left or right, total distance is keeping track of all that motion and adding up all of the moves that I'm taking. So total distance is going to be an integral as well of velocity from A to B, but to capture all my movement and make all my negative steps count as positive steps, I want to put the absolute value on that velocity function. So these are just really important formulas for us to internalize. And in this problem, we've got a particle moving along the x-axis with a given velocity function, and we're asked to find the total distance from 0 to 3. So if I just populate this new formula for total distance, my integral is from 0 to 3 of the absolute value of 6t minus t squared dt. And typically these are calculator active problems, so I've come over here and gone ahead and typed 6x minus x squared in my graph. I'm going to come to a calculator page and get my integral established, 0 to 3 of the absolute value. You can just type abs in your calculator, it'll understand what you want. And you can either type in 6t minus t squared dt right here, or I already put that in f1 of x, so I can just type that. And the answer is 18. Ignore that. Come back over here, record my answer, and I'm done. All right, and my final key lever here involves speed. So I want to talk to you a little bit about speed being increasing or decreasing, and then answer this question. So one way of rephrasing speed increasing, College Board oftentimes will say, where is it that your particle is speeding up? So that's a big thing that they like to say. And my particle is speeding up, we've talked about this before, when velocity and acceleration have the same sign. So we're looking for either both positive or both negative when we see these phrases. And then alternatively, we could also be asked for speed to be decreasing, which another way of phrasing that is when is our particle slowing down. That's another common phrase they like to use. And that would be when velocity and acceleration have opposite signs. So this is the big guiding force to help us out on speed questions. On this particular problem, we've got a velocity function, and we're given some info about it. It's defined for 0 to m. We've got some constants. We intersect the x-axis at a few places and have horizontal tangent lines. We're asked to find when the values of t represent decreasing speeds. So I want to try and find when my speed is decreasing. And when I think about that, I'm relating that over to this big idea over here on the right. That means that velocity and acceleration need to have opposite signs. Well, this is a velocity graph, so I should be able to at least identify, it's pretty straightforward, when velocity is positive and when velocity is negative. So let me use some color here. This top chunk of graph, I have velocities that are above the x-axis, so in red, that's when my velocities are positive. That's a plus sign. And then down here, of course, we dip below the x-axis, so that's when my velocities are negative, which is great. That's really, really helpful, but that doesn't yet indicate anything to me about the sign of acceleration. That's where the rigor comes in on this problem. So I want to think about my stairs for a quick sec. Position, velocity, and acceleration. all I have access to in this problem is a velocity graph. And for this particular problem, when I'm up here in red, for that velocity, since that velocity is positive, and I want to know when the speed of the particle is decreasing, what I'm really trying to ask myself is, on that red stretch of graph, is there anywhere where the acceleration is negative? Because if the answer is yes, then I would have positive velocity and negative acceleration, leading to those opposite signs and an answer to the question. So I have to think critically about that. What does it mean for my acceleration to be negative if I'm looking at a velocity graph? Well, I head up my stair, and if acceleration is negative, that means the velocity has to be decreasing. And is there anywhere on that red stretch of graph where I have a decreasing velocity function? There absolutely is, right here from J to K. So there's one answer to my question. Between J and K, I have decreasing speed because the velocity and acceleration have opposite signs. I think there's another place where I can get an answer to this question too, but it's going to be down here in the blue graph. I am not considering anything in here between 0 and J, because although my velocity is positive, my velocity is also increasing, which means the acceleration is positive. We have same signs there. That's not what I want. So let's go to the blue chunk of graph. I have negative velocities down here. It sure would be great if I could find somewhere in that region where the accelerations were positive, leading to the opposite sign bit. So when I start at K and I move down to L, I'm asking myself, well, what's velocity doing right here? Velocity is decreasing, right? That means, like we established earlier, the acceleration's negative. It's not what I want, because if acceleration's negative, we see the same sign. But keep going from L all the way to M, and oh my gosh, what do I see? I see increasing velocities, which means if velocity is increasing, the acceleration one step below has to be positive. And that's what I'm looking for. So another location where my speed is decreasing is between L and M. And this is because of our annotations, because velocities and accelerations have opposite signs. All right, tune into the next video and we're going to do a model problem all the way through.